All right, welcome, boys and girls. This is assignment 7M, and it is entitled Areas and Volumes. So I'm guessing this is just kind of a review of all of the different areas and volumes that we may have found, and I'm assuming that it's also going to probably involve some sort of calculator stuff. It's looking like it's kind of a large assignment, so let's go ahead and get right down to it and start handling some of these problems. Okay, so we begin with areas. And so we're asked to find, choose the alternative that gives the area of a region whose boundaries are given by. Okay, so here we go. So we have y is equal to x squared. So this is our x squared. And we have y is equal to 0. So y is equal to 0. And x is equal to -1, x is equal to -1, and x is equal to +2. So we have a couple different areas described here, but luckily it's all the same top and the same bottom, so it's just fine. So this area is going to be the integral from -1 to +2 of x squared. All right, so we have this set up. Let's go ahead and knock it out. So this is going to be 1/3 x to the third. And so this is 1/3 of what? 8 minus -1. All right, here we have x squared minus 3, so that's a parabola that's down 3, and y is equal to 1. Okay, so this is the area described, not a big deal. Where did they intersect, though, is kind of a big deal. So where is x squared minus 3 equal to 1? And so that's where x squared is equal to 4, and x is equal to plus or minus 2. So that lets me know where my integration has to start and stop. That's why I did that portion of the problem. All right, so this area is going to be the integral from -2 to 2 of the top, which is y is equal to 1, minus the bottom, which is x squared minus 3. All right, so this is -x squared plus 4. So this is -1/3 x to the third plus 4x. Assuming it's the exact same answer, just negative. Two-thirds. Okay, y squared minus 1 is a sideways parabola opening in the positive direction, so it would look something like this. And the y-axis, which is obviously this. So doing some simplistic math, I need to know where y squared plus 1 is equal to the other line, which is at 0. And so y is equal to plus and minus 1. That's where my integral starts and stops at positive 1, negative 1. And this is a dy kind of graph. I'm going to be integrating with lines that look like this. That's a dy style. All right, so this is going to be the integral from negative 1 to 1 of y squared minus 1 dy. So this is 1/3 y to the third minus y from negative 1 to 1. Ooh, I see. Ooh, okay. Close. This is still this line is technically x is equal to 0. All right, so the big minus the small is technically the right minus the left. The big minus the small is technically the right minus the left. So this integral, yes, is from negative 1 to 1, but the big is technically 0, and the small is technically the y squared minus 1. So now that is the right minus the left right there. That's the right minus the left. So this is negative y squared plus 1. So this is negative 1/3 y to the third plus 1y. All right, I'll get both of these equal to x. However, this first one I'm just going to get an idea of. So this is negative x plus 2. That would kind of just help me graph the stuff. So we have this y squared, and then we have this positive 2 negative x kind of dilly going like this. But now I am going to solve this for x, which is kind of like that. Now I need to find out, so because I have them, I'm going to be integrating this style, which is a dy style. I need to know where to start and stop my integration. So where are these things equal to each other? So where is y squared equal to 2 minus y? So it's at negative 2 and positive 1. So now I know where to start and stop my integration. Okay, this is a dy, and again, this is going to be the right minus the left, so it's blue minus red. All right, so we're going from -2 to +1 of the blue, which is 2 minus y, minus the red, which is y squared. Okay, easy peasy. Oh, this stupid problem. Oh, this stupid problem. All right, this graph looks like this. This is what this graph looks like. This maximizes at +2, -2. This is 0. Okay, what I'm going to do is I am going to figure out the area of this portion of the graph, and then I'm going to quadruple it. I'm going to multiply it by 4. Right? And so this part of this section is the positive square root of y squared 4 minus y squared. All right. So if this is true, this is just y 4 minus y. Nope. I'm sorry, it's not squared. I'm sorry. It's y squared. So that's what that portion of the graph is. Okay, so to get this area, minimize this a little bit. All right, so this is going to be the integral from 0 to 2 of y 4 minus y squared to the 1/2. Now, that is still pretty difficult, so we need to probably do a u substitution in this problem. So let's go ahead and set up our u substitution. So u in this situation is 4 minus y squared. That means du is -2y dy. So I need to multiply this by -1/2 in this situation. Um, okay, oh, sorry, there's also a 4 out here, because I need 4 of these areas. And the integral 0 to 2 is now going to be what? 0 on top and 4 on bottom. All right, so this is now updated. This is 4, there's a -1/2 that needs to come out, integral from 4 to 0. I know it's backwards, but it's just the way it is. And this is going to be u to the 1/2. All right, so u to the 3 over 2, 2/3. This is on the -2 that's already on the outside from 4 to 0. This is 0 minus 8. And so this is positive 32 over 2. That one's a pretty tough question. That one will get you. Okay, hopefully the others aren't as rough. So this is going to be 4 divided by x squared plus 4. Okay, we got this bump thing. Oh, I know what we're doing now. Oh, this from -2 to 2. All right, so what I see this as is I need to take the derivative of the integral of a squared plus u squared du. That's what this is. And so this is going to be 1 over a inverse tangent of u over a plus c. But because this is a definite integral, we're not going to get the plus c. Okay, so we just kind of have to manipulate that bottom that is currently there. Stash this right here. Okay, so what we have is my a squared is 4. That makes a equal to 2. U squared is equal to x squared. That makes u equal to x, and du is equal to dx. Yep. All right, so the only thing that I can't really figure out is this 4. So I'm going to take that 4 to the outside, and then I think everything will be good to go. It's also worth noting that -2 is still -2, and 2 is still 2. All right, so what this problem becomes is 4 integral of a squared plus u squared over 1 du. Okay, doing basic substitutions from -2 to 2. Okay, so this is going to be the inverse tangent. So this is going to be 4, 1 over a inverse tangent of u over a. U stays the letter u, so this is going to be 1/2 u. In the world from -2 to 2. All right, so two math problems. One of them is when I put in the 2, so that's going to be the inverse tangent of 1. And so that's the tangent is equal to 1. That's going to be a pi over 4. This is where sine is equal to cosine. And the other one is where it's equal to negative 1. And again, that's where sine and cosine are equal but opposite signs, and that's going to be at negative pi over 4. So this is going to be 2 pi over 4 minus negative pi over 4, which is pi over 2, but times 2, so this is just straight up going to be pi. I'm going to write these as x's. It doesn't really matter. X squared minus 5x and 3x minus x squared. Okay, cool. And I'm just gonna keep them as these x's. I have this upside down parabola, this right side up parabola, something like that. And again, all I did is I just said like y is equal to x squared minus 5x, and y is equal to 3x minus x squared. It doesn't matter if you take the reciprocal of all letters, it's all good. And so in this case, I'm going to dx this. I guess it's not technically right, but again, I don't think we have to really show a whole lot of work on this. The intersections occur at 0 and 4. Intersections occur at 0 to 4. So this is going to be 0 to 4 of the red, which is the upside down parabola. Minus the right side up parabola. And then this is technically d1. No one is none the wiser that I didn't graph it the way that I was supposed to graph it. So this is negative 2y squared plus 8y. Okay, this is a teeny tiny little sliver of a graph. So the 2 over x comes swooping down like this, and the line just barely nicks it. I'll draw it a little bit more drastic than what it actually is, but it just barely nicks it. And so it does create an area right here. And so let's go ahead and figure out where this starts and stops and figure out stuff. So let's count 5. 6, Okay, so this is at 1 and 2. Okay, and this is the line over the, it's not a parabola, but the swoopy thing. All right, so this is going to be the integral from 1 to 2 of y is equal to 3 minus x over the 2 over, which is minus 2 over x, or 2x to the negative 1. All right, so this is going to be 3x minus 1/2 x squared minus 2 ln of x. From 1 to 2. All right, so let's plug in 2 just to the number portion of this. So the numbers are 3x minus 1/2 x squared. Let's just worry about that. So that's 4 minus 2 ln of 2 minus 1 is 5 over 2 minus the minus 2 ln of 1. ln of 1 is equal to 0. So this is 3 over 2 minus 2 ln of 2, which again you can put up into that equation. So this would be the same thing as saying 3 over 2 minus ln of 4. So again, describing what that was, it becomes an exponent. In the first quadrant, bounded below by the x-axis and above by the curves of sine and cosine. Okay, so again, sine looks something like this. Cosine looks something like this. So it is bounded below by the x-axis. That is the bounded below and above. So we're technically talking about these curves, right? That curve right here. So this first intersection, this is going to occur at pi over 4. And the second, where this area ends, is at pi over 2. I think that's how I read this question. Let me just kind of take a look here. Yeah. That's how I read the question. That was the area that I figured out. I'm not sure if I am, because my other concern would be this. No, okay, so this is the only one that is bounded below. It could technically be this area too, but I really, really, really doubt it. I think this is what they're trying to describe. Okay. So the first part of this is of the red line, the sine. and that is going to be the integral from 0 to pi over 4 of the sine. And to that, we need to add the area of the blue, which is the integral from pi over 4 to pi over 2 of the cosine. All right, so sine goes to negative cosine. Cosine goes to positive sine, no problem. Let's get a unit circle in here. All right, so we have 3 important angles here. So we have 0, which is 1, 0. We have pi over 4, which is square root 2 over 2's. And pi over 2, which is 0, 1. Okay, so the first one is going to be the cosine of pi over 4, square root 2 over 2, minus the evaluation at 0, cosine is 1. Okay. Plus the sine at pi over 2, cosine sine is 1, minus square root 2 over 2. All right, so we have negative square root 2 over 2 minus 1 plus 1 minus square root 2 over 2. This is the obvious simplification here. Whoops. Whoops, 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 whoops. No, I did that right. Hold on. I did do this wrong, sorry. This is negative square root 2 over 2 plus 1 minus square root 2 over 2. All right, so this is going to be 2 minus square root 2. But I made a slight mistake on this. I didn't bring it in. That's well, I kind of did, but I kind of did. All right, so this is the classic problem. So again, sine looks like this. Cosine looks like this. And they want to know this, which is from pi over 4, which happens to be where that occurs, to 5 pi over 4, right where that occurs. This is the classic problem. So this is going to be sine over cosine. So this is going to be from pi over 4 to 5 pi over 4 of the top, which is sine, minus the bottom, which is cosine. Sine goes to negative cosine. Cosine just goes to a straight sine. All right, let's start taking a look at a unit circle to get some of these values here. Okay, so we have pi over 4 and 5 pi over 4. So this is what, square root 2 over 2, square root 2 over 2. This is negative square root 2 over 2, negative square root 2 over 2. Okay, so we begin with the 5 pi over 4, which is the negative square root 2's. So that's going to be a positive square root 2 over 2 plus square root 2 over 2 minus the square. negative versions. So negative square root of 2 over 2 minus square root of 2 over 2. All right, so this is square root of 2 plus square root of 2. This is 2 square root of 2. Volume now. All right, so we have y is equal to positive x squared, x is equal to 2, y is equal to 0, about the x. All right, so I'm going to integrate this up and down, which is a dx. Rotation about the x is a dx. So this is going to be the disk method. This is the pi r squared method. So this volume is going to be pi integral from 0 to 2 of x squared squared. So pi r squared. So this is x to the 4th, 0 to 2 pi. This is x to the 5th, 1/5. 0 to 2. This is 1/5 pi of 2 to the 5th, which is, I think, 32. 32 minus 0. So this is 32/5 pi. All right, so again, we have another parabola. We have x is equal to 2, y is equal to 0. But this time it's about the y-axis. So I'm still going to integrate the same way. So this is a dx. However, this is rotation is a dy. So this is implying that I should probably use the shell method, which is this 2 pi integral, and then it's like x times the function kind of idea. So it's 2 pi the integral of x times the function. Pi of 16 minus 0. At least you're consistent. There we go. So we have an x squared. X is equal to 2, y is equal to 0, about the line x is 2. All right, so again, I'm still going up and down dx. This is still a dy, but the spot is manipulated. So this is going to be 2 pi integral 0 to 2. So again, 0 to 2 is defining what my x is going to be. So when I have to make a decision, is this going to be x minus 2 or is this 2 minus x? Okay, is this going, what I'm saying is this going to be x minus 2 or 2 minus x? Again, x is a number between 0 and 2. So if I want this to be a positive number, I would have to choose that version of this part of the problem. So this is going to be 2 minus x. And then it's just the function just as it normally is. So this is going to be 2x squared minus x to the 3rd. Okay, so this is very specifically in the first quadrant. X squared, y-axis is the other boundary y-axis, and y is equal to 4. So this is a unique way of doing this. So I'm going to probably turn this into the square root of y and integrate this stuff right here, which is going to go from 0 to 4. This is going to go around the y-axis. So my way of integrating is a dy, and this is a dy. So these match up. So this is going to be the disk method, which is the pi r squared method. Kind of works out pretty nicely this way. All right. No really good way of graphing this. So this is the area that's described. And so to ensure that I have one over the other, I need to integrate up and down. So this is going to be this is a dx style of integration. This rotation is a dx. So this is going to be the pi big R squared minus little r squared kind of method right here. It's the disk method, but there's two radii right here. Where do they intersect? 2's and so quick math. This is going to be -2 to a +2. So the big radius, the one that is furthest from my axes of rotation, is the line. So that is 4. The little radius is the x squared. Okay, it looks like they just want us to set this up. All right, so we have this x squared, y is equal to 4, about the line x is equal to 2. All right, so again, this does exist from -2 to +2. So again, the best way to describe this area is to do an integration this way. So my integration is going to be dx. However, if they want me to revolve this around a line x is equal to 2, that's a dy style. So this is best accomplished by doing the shell method, which is the 2 pi integral x minus, or excuse me, x times the function. But again, I obviously have to adjust the integral so I can ensure that this is going to be positive. Okay, so the volume of this is going to be 2 pi integral negative 2 to 2 of x. So I'll fill in the blank here in just a second. The function is x squared. Now again, I have two different options. I can go 2 minus x, or I can go x minus 2. Again, to ensure that I have a positive number, the way that you would probably want to do this one is do the 2 minus x. So for instance, when x is negative 2, this would be 2 minus negative 2, which is great. But if it was like negative 2 minus 2, then that's not so great. So this would ensure that it's positive. So this is the setup right here. Let's just see if it rings any bells here. Oh, no, I'm sorry. Okay, so yes, this is 2 minus x. However, the area that I'm describing has to be the top minus the bottom, which is technically 4 minus x squared. I'm sorry. So negative 2 to 2, 4 minus x squared, 2, yeah, that fits all the bills right there. Okay. Okay, so back to actually doing these problems, we have an x squared, y is equal to 4. Did I do this upper one correctly? Yes, I did. All right, so again, this is my area. How I'm going to do this is this method, which is a dx from negative 2 to 2. And then they want me about the line y is equal to 4. Y is equal to 4 is up here. But it is a dx method, so I am going to do this with the disk method. And so again, that is pi r squared minus r squared. And recall how to adjust the axes is you subtract. So there'd be like a minus 4 in with both of these. Because they're squared, it doesn't really matter. And the big radius is now the parabola, the little radius is now the line. All right, so the big radius is the parabola. So that's the big R minus the new axes squared. So that's the big R squared minus the little r squared. So that's kind of fortuitous. Notice how that's a 4 minus 4. Cool. So this, I'll just eliminate that portion to make it easy on us and say that's dx. So this is x to the 4th minus 8x squared plus 16. All right, so the big radii is still, it goes back to that 4, and the small radii is now the parabola. These are both dx methods, so this is going to be the little, excuse me, the big radius minus the little radius, so pi r squared method. All right, so let's just set this up. I'm not sure. Okay, I'm thinking too hard. Let's just see what we can figure out. So this is pi integral from -2 to 2 of the big radius minus the new radius squared minus the little radius minus the new radius squared. So this is technically 5, so this is 25 minus x to the 4th. This is a +1, so plus 2x squared plus 1. It's not looking like anything that I want. Let's keep going. Let's see if it hands out. Okay, I see their stupid trick. Okay, here's their stupid trick. All right. So what they're going to do is they're going to look at that as the square root of y. Okay, so there is another portion to this. All right, so here's my grand thought. Okay. So what I'm going to do is this. I'm going to technically integrate this way just on this world that is right here. So I'm totally ignoring this left-hand side. Okay, I'm just going to totally ignore that. And again, this is going to be revolved about y is equal to -1, which is a dx type method. However, I'm integrating in a dy method, and this is from 0 to 4. All right, now this will only give me half of the volume that I want. So what I'm going to do is I'm going to find this volume and then just double it. So starting with what I have, right? So the volume, just forget about doubling and everything. It's just going to be 2 pi integral 0 to 4 of y, and then this is the square root of y dy. Okay. Now again, I have two different ways that I can go about this. I can go -1 minus y, or I can go y minus -1. Again, to ensure a positive answer, y is a number between 0 and 4. This would be the method right there that would ensure a positive number. So this is going to be a y plus 1. Okay, now, this is only going to get you half of the volume that you wanted. All right, so what we need to do, if this is getting you half of the volume, is double. And so ultimately, this is going to be 4 pi 0 to 4 y plus 1 square root y dy. Let's take a look at this picture. That line doesn't belong there. All right, so this is not sure where that's equal to. So this is where is 3x minus x squared equal to 0. And so this is going to be x squared minus 3x equal to 0, which is 0 in positive frame. All right, so for simplicity's sake, this is how I'm going to integrate, which is a dx style, and we are going about the y-axis, which is a dy style. So that is going to be the shell method. That is the 2 pi, and then x times the function kind of by the end. Right, so this is going to be your regular disk method. So this is the pi r squared method.